we'll have Gerardo Acosta from INTELYMEC-CIFICEN. His presentation is going to be application of aquatic robotics in the exploitation of marine energies. Please.
Well, I'm going to give you a talk about the applications of aquatic robotics in the exploitation of marine energies. I don't have the... First of all, I would like to generally speak about the types of aquatic robots that we are talking about. We have a family of robots that are autonomous underwater vehicles, or AUVs, which main features are that they can operate without a physical link with an operator. And they are also autonomous, not only regarding the decision-making of the first point, but also regarding the energy, as we will see. They have a very limited communications capacity because we can reach these robots and they can give us data through acoustic channels, and we are limited in the bandwidth. They are typically torpedo-shaped vehicles, like we can see here in these figures. We can see here some vehicles developed in our groups. I omitted to present my co-author, that was Nuno Cruz. He is with the INESCTEC group in Portugal. They developed the three mares, the mares, and many aquatic robots. And this one was developed in our group here in Argentina. They, as a main feature, is that they can charge many options of payloads. That means a lot of sensors and a great variety of sensors, from sonars to camera, water quality sensors, and so forth. Regarding the autonomy, they have the possibility to develop missions of tens to hundreds of kilometers, and from hours to days. Even though they are not a highly mature technology, there are more than hundreds of these kind of vehicles in operation all around the world. Regarding the present application, some pros are that they can operate from very shallow to deep waters. They have a great maneuverability to acquire data in a 3D distribution range. And they have the possibility to have motion relative to the bottom, so they can get close to the objects that we want to analyze, to collect data, to inspect, and so forth. And a great advantage is that they can need few personnel involved during these surveys. Regarding the cons, we have, as I told you, a limited communication capability. They are relatively complex to operate and maintain, even though we are doing great efforts in the user interfaces to improve this point. And there's still a lack of standardization in mission programming. Another group of aquatic robots are the gliders, that we have autonomous underwater gliders that can be considered as a particular case of autonomous underwater vehicles. But perhaps the main feature is that they can save a lot of energy in the navigation, because they have a principle of operation based on the difference of buoyancy, and they go flying in the water. This gives us some kind of yo-yo trajectory that goes slowly straight forward. They have a very long range autonomy. Of course, this is something that depends on the payload, because if you put sensors that are highly energy consuming, you won't have a wide endurance for the batteries. And regarding the communications possibilities, they are intermittent. When in the surface, they can have, or we can have access to them by radio frequencies, and when down, we can communicate by acoustic links. They are very good for acoustic recording because they are very silent. They navigate quietly. And of course, they have no possibility of intervention. I mean, they are only for data collecting. Okay. Another kind of robots are the autonomous surface vehicles. That one of these are presented in the previous presentation by Patricio. They can operate without physical link to the operator, and the same as AUVs. But they have the possibility also to be teleoperated by radio frequencies links. And they have a good energy autonomy because we can have some kind of energy harvesting from solar or wind to make them complete missions with more endurance of batteries. Here we have an examples. This was developed at the INESCTEC. This one was developed here in Argentina by the group of Patricio and Ignacio and Juan de Linar. And this also was developed in our group, the Macabot, and they are good examples of this ASV. Regarding the advantages, we have that the possibility of real-time communications, a precise geolocalization of data, because we have access to differential GPS, Arctica, and so forth. They can be made very, very fast for navigation. And in the same way of AUVs, we have many options for payloads, including intervention possibility. I mean, we can have manipulators on board to make some simple tasks. Regarding the disadvantages, we only can sample the surface layer of the oceans, of the water volume, even though we can extend this area of survey some meters below. They are useful also when trying to assess the quality of fresh water for cities with this kind of sensors of CTDs, for instance, to have some measurement of some interesting variables of the water volume. They have a limited range of operation, and the maneuverability of this kind of robots is not as good as others that we will see. So they are, we can say that they are difficult to operate close to structures. A special case of this are the wave gliders that, as the underwater gliders, has the same advantage of a very low energy consumption. They leverage from the principle of wave energy conversion with this device that is pulling from a surface vessel, and with the difference of the waves, it can go navigating straight forward. And of course, even when they are slow vehicles, they can navigate with an unlimited endurance, and their final velocity depends on of course, on the wave amplitude and frequency. The other kind of aquatic robots are the ROVs, or the remotely operated vehicles. They are remotely controlled, so they require a human operator. Even though they can have a limited autonomous behaviors, like, for instance, speed of approach to a platform, or maintaining a preset depth in operability. They have the advantage that the energy, as they have this cable to be controlled, can be provided by a surface vessel. So in principle, we have the possibility of have enough power, and also the possibility to transmit data. Their sizes vary from a few kilograms, like this Scout of video ray, to tons, very huge and heavy robots, depending on the payload. As you can see, the shape is not designed to navigate, but they are designed to transport a lot of sensors and propellers to cope with different environments and operative situations. They can have, regarding the advantages, they can have a high availability of energy, variety of payload, as I mentioned, data transmission, and these kind of robots are the best tool for interventions. Regarding the disadvantages, we need a human operator for the mission, and also the cable, as you go deeper, limits the range of operation, the quality of the control, because it disturbs the motion, and you are limited by the length of the cable in the range of operation. Regarding the applications and potential, we can say that we divided this talk before the deployment of marine infrastructures. during the deployment of marine infrastructure and after the deployment. Before the deployment, these vehicles can be useful for optimal energy production locations determination and to make the assessments of environmental impact, for instance. During the deployment, they can support the infrastructure construction. And after the deployment, they are very useful, as we will see, for operation, monitoring, and maintenance, and also for research and development of marine energy technologies. Regarding the optimal energy production location, aquatic robots are useful to study specific variables that can give us some feeling of where we can locate the infrastructure, because we can collect data about tidal, wave shapes, thermoclines, temperature gradients, speed of waters, and so forth. And also we can carry out surveys about the seabed morphology and the composition when we need to anchor infrastructure, and collecting data about water quality, features, and ecosystem of marine life in general. So for this point, the best option for this stage are AUV, ASV, and gliders. For the support of infrastructure construction, we need intervention. So the best option for this is ROVs, because we have availability of arms, powers, lightning, and so forth in the underwater world. Then, during operation, monitoring, and maintenance of infrastructure, we need to optimize the survivability of the equipment of the whole infrastructure. We can see here some of these layouts. And aquatic robots are good to obtain images, video or acoustic, to evaluate the state of the energy converting device, to prevent damage to species also, to be ecosystem friendly. They are good to make surveillance to prevent vandalism and attacks, and any other factor that could put at risk the production and supply of energy. These vehicles that are good in this stage are AUVs, ROVs, and also, as we can see in the previous presentation, a combination of these kind of autonomous vehicles could be good for maintenance of this infrastructure. Also for data update in digital twins for remote monitoring and operation of the infrastructure. When researching and development of this technology, they are, for instance, we have here an AUV observing directly and closely how the technology is doing in the runtime. And also they can leverage from the marine energies to recharge their batteries. There are many docking stations to do this task, and this will enlarge the endurance of batteries and the possibility of longer missions. I put here some example of a docking station that is taking advantage of wave energy that was developed by University of Hawaii. Regarding future perspective, there are many topics that we can think about in cooperative robotic, digital twins, advanced robotics, perception. human and robot collaborations with the use of large generative language models that will allow us to cope with a complex situation like we have in a typical infrastructure layout for marine energy production. And as you can see, we will need data and perspectives of the normal runtime of this infrastructure from different points of view, and robotics can facilitate this situation. And which are the open issues that we can identify for now in this area of robotics? We are proposing that we have to take advantage of the advances of artificial intelligence, particularly for the development of advanced perception systems and decision-making systems, mainly for the dynamic replanning of actions of this kind of cyber-physical system integrated by many robots. So we can perform and optimize their task in this changing environment like the oceans. And particularly we are focused on advanced perception and decision making. So regarding this, we can make some new technology and new ideas to move the frontiers of this knowledge regarding the navigation, guidance, and control systems with resorting to artificial intelligence, and also for decision making. We are we were working with the construction of digital twins, which is a tool that is being in use, for instance, for the oil and gas extraction in the sea, to make monitoring and maintenance of this infrastructure. So, well, these are some examples of possibilities of application of artificial intelligence in these modules or subsystems of an autonomous robots. For instance, the visual localization and mapping using grid and place cells, and also the design of advanced perception systems with multiple sensors doing the fusion, also with neural networks and deep learning, and some interesting applications, maybe bathymetries to the seabed, and also the recognition of objects in the infrastructure to build the digital twin. So my concluding remarks are that the growth of offshore renewables really poses exciting challenges for the community of robotics. There are, as we have seen, many approaches that are working now, like for the wind energy installations with drones, for instance. And we think that we have a possibility with this wave and solar energies that somehow are emerging technologies regarding the marine energies. And maybe that we can grow together integrating advancements of both technology, because requirements from a new field can be of use for robotics. And as I mentioned recently, the current research in artificial intelligence and robotics seems to be breakthrough concepts in marine operations, like the case that we are studying now. So thank you for your attention, and we can proceed with the questions.
So thank you, and there's time for one quick question. There's Mauro and John. Start with John.
Thanks. I'm just interested to know, for the recharging stations for the UAVs, how do you imagine those will be powered? Will they be powered with marine energy, the recharging stations?
Yes. You have a docking station that
the mic.
provide energy.
The mic.
You have, sorry, you have a docking station where you have the possibility to store energy, and you have to be in communication with the AUV, for instance, or the surface vehicle as well, and you can get available that energy with a special plugs that you have to localize from the AUV to make the charging of the battery of the robot. This may be a slow procedure regarding, I mean, it's not like when you are charging your smartphone, but this allows you to make very long range, long time missions. So it's worth it to wait some hours to recharge your robot, because you can operate continuously.
Well, I'm just wondering what the power source is. Are you using the power of the waves or solar or?
Yes, we can use solar sources, solar energy, and also, as we see here, wave energies from the movement. You can have well, I cannot explain this to you, but this is a device that is getting advantage of that.
But I guess the interesting part is that in wave energy, you generally, to harness a lot of wave energy, you aggressively move the device, while for docking, you want the device to be as stationary as possible, right? So there's an interesting problem to be addressed there, but not unfixable, I think.
Okay.
Thank you.
Thank you.
Thank you.
So, is it very quick one, or? Yeah, we can discuss it about later. Yeah, cool. See, thank you again.
Okay, thank you very much.